What I thought I should talk about here is, and just clear up a few terms, is electric field, electric potential, and potential energy, all different things. Now, we already know that around a charge, we get something called an electric field, right? And we all know that's what generates this force on a charge. The charge doesn't have to be moving. Remember, I think, or you may not know, we'll get to it when we do electromagnetics, but when you get these, you know about magnetic fields. And when you've got magnetic fields, maybe you've got a big magnet here, and we said that the magnetic field goes from north to south like this, right? Now, when a charge moves in a magnetic field, it experiences a force, but it's got to move at right angles to the magnetic field. We've found, and if you didn't quite get that, that's okay. We've found that a charge doesn't even have to move to experience a force in an electric field. Doesn't need to move to experience a force, right? An electric field, a charge. So this is all part of it being statics. Doesn't need to move to experience a force. Now, that's the electric field. Potential energy, V equals energy per charge, right? We did this where we said energy equals EQD, and we were calculating how much energy a charge gained or lost when it moved in an electric field. That's just like potential energy in when you lift something up in a gravitational field. So that's just potential energy. So on this, hopefully these two are quite clear. What confuses people sometimes is it's sort of like a combination of both. Electric potential, and we often tack on the end, electric potential difference. Electric, or there's another one, electric potential difference, or EMF, electromotive force. They all mean voltage. Now, voltage is not potential energy. Voltage is, as we've seen, energy per charge. And I'll just get another bit of paper, but when we look at energy per charge, it's something we don't use when we're talking about gravity, but it's a little bit like this. First thing I'll show you, we've got an electric field. What we can find is that we've got what are called voltages. So away from this positive charge, I might call that 20 volts, and I might call that 10 volts. Now, that's because as a charge moves in an electric field, right, from here to here, so a positive charge will move from here to here, right? It loses potential energy, all right? Now, the potential energy it loses, this all gets a little mathematical, but I'm going to try and give you a way of thinking about it. We said that energy equals EQD, all right? So, energy per charge is actually equal to ED. So, E, which is the field, times the distance here is the amount of energy per charge that was gained or lost. And believe it or not, we have a word for that, and it's volts. So the energy per charge that is gained or lost when you travel in an electric field is called volts. Now at this stage I'm sure you're going, oh god, that just was too much. It's a little bit like this. Let's look at the gravity situation. When you lift a mass up, it gains energy, mgh. Now we might go, okay, well I just want to know at certain heights how much energy is gained or lost per kilogram. So I would just divide that by mass, and I would have something called a GH. Now GH with gravity is exactly like what volts is. It's the energy change per kilogram. With volts, you've just got an energy change per charge. We don't have anything for GERs like GHs. And we could call them smabbles or something. What's the smabble change when you lift something up? Just some ridiculous word. We just don't have a word for it. But with electricity we do, and it's called a volt. And it's energy change per charge over a certain distance. And we certainly have that with gravity. Energy change per kilogram over a certain distance. We just don't have a word for it.